couple months, and I'm going to show you around a little bit. Obviously the throughput is kind of loud, so a lot of this is going to be voiced over. This here is my chemistry station. I've got some ferrofluid, spheric particles suspended in water. I've got some hard disk drive. I don't know if you can see that. These have magnetic fields printed onto them, very high gradients of the surface. I've got some PVA solution. This is essentially just Elmer's glue, but it's clear. And I've got some other stuff that I don't really use that much. So these here are prepared samples. I've got nanoparticles suspended in the PVA as a polymer substrate, and then Scotch tape mounting them onto just a little threaded disc there. The nanoparticles assemble on the disk drive media into these cool little microstructures that are just over a millimeter wide. Shining a laser through them will cause the light to diffract, and I'll get a pattern that I can use to learn more about the structure. After they assemble, I spin coat the disc with some polyvinyl alcohol solution, which easily peels off. Over here is my optics board. I've got a fiber optic cable, just a light source here that I can turn on. Several lenses, an iris to block out light, a helium neon laser, and just several other laboratory tools and components. The main setup is a helium neon laser, which is incident on a focusing lens. The focused laser beam is aimed at the PVA peel, which is mounted on a little makeshift setup. I sort of jumped the gun by immediately adding a Fourier lens. In theory, it would make finding the Fourier plane much easier, but the lens was a bit dirty and lining everything up is always a challenge. Ideally, you want everything to be in a straight line, keeping the beam exactly centered on the lens and at perfectly normal incidence. As soon as I turn the laser on, you can immediately see two red dots pop up on the sample mount. This is caused by the laser reflecting off of both sides of the lens as it passes through. I tried to line it up by measuring using my paper ruler, but the easier way would have been just trying to get the reflection dots as close to the objective beam as possible. Since perfectly normal incidence always reflects back at the source, this would have been the best way to check on both sides of the lens. When I was sure that I was actually getting a diffraction pattern, I set out to find the Fourier plane, where the diffracted image is actually focused. Unfortunately, I was getting some dots that weren't even part of the diffraction pattern, and as you'll see in the next couple images, the lenses were causing a lot of spherical aberration and I couldn't find the Fourier plane at all. Those three dots surrounding the center are just reflection dots, and overall it was just pretty blurry. I wanted to try just using an iris instead of a focusing lens, which would cut down on the intensity of the objective point, but it would at least be collimated light, and I wouldn't have to worry about focusing it as much. As I was adjusting the size of the aperture, I noticed some funny business going on the other side. It appeared as if the laser beam diameter was changing size as I changed the size of the iris opening. This was again just the laser beam reflecting all over the place. This is actually one of the reasons why working with a laser can be kind of dangerous. It can reflect right back at you even if you think you have the laser pointed in the other direction. Luckily, this was a simple fix, and I was just going to have to rotate the sample mount to get the reflection to shine right back through the iris. After messing with the aperture size a bit more, I cranked it down and set out to find another diffraction pattern, hopefully less messy this time. Even though I was certain I was shining it directly at the particles, I was still getting those annoying reflection dots above and below the center, and I was going to have to do something to fix it. I tried to add a Fourier lens again, but things weren't really going as planned when I tried to find the Fourier plane. There seemed like there was all this random speckle, it was still pretty out of focus, and I had only added more internal reflection dots. I ended up scrapping the Fourier lens, messing with the alignment of the focusing lens, and settled on the fact that I was going to have to use the iris and the focusing lens at the same time. I came back the next day and decided I needed a better sample mount. I wanted to be able to pan the sample around to the objective beam in both the X and Y axes. I have these nice little translation stages that I had rigged up incorrectly the first time, but orienting them in the way that I wanted to was proving to be a little confusing. In the end, I was satisfied with this as my final design. I could now move the sample up and down, rotate it in the mount, and move it laterally across the objective beam. When I turned the lights off, I saw some perfectly focused second-order diffraction maxima, and as I panned around the sample, I started to get all kinds of cool patterns. Since I didn't really care what the central maxima looked like, I decided to punch a hole in the middle with my Allen key to let that excessive light go through. I thought some of these patterns were really interesting, especially when it seemed to make a perfect image of the particles. I'm pretty sure that can't happen because what I was really imaging was the spaces between the particles, but it was still kind of throwing me for a loop every time I looked at it. As I continued to pan around the sample, it began to split into these bands, sometimes 3, sometimes 5, and in different angles as well. This pattern here is also especially interesting to me because when I take a binary image of the particles and then do a Fourier transform of the spaces in between them, the resulting Fourier pattern looks a lot like what I was seeing in the diffracted image, especially when I crop out the phase data. I'll do my best to keep you updated on the rest of this project, but for now I'll just leave you with some nice piano music and laser speckle.